In this lesson, we'll take a detailed look at the fetch, decode, execute cycle. The fetch, decode, execute cycle is also called the von Neumann architecture, because it was originally conceived by the Hungarian-American computer scientist John von Neumann. Von Neumann's big idea was to store a program in the main memory of a computer and fetch each instruction one at a time into the central processing unit to be decoded and executed. In 1948, the Manchester Baby was one of the first computers to demonstrate von Neumann's stored program concept. The Baby soon became the Manchester Mark I, and it included many of the features of a modern computer. It had a random access memory, it stored programs and data in binary, and it had a separate CPU that could handle about 1,100 instructions per second. OK, so a modern computer, even a smartphone, can handle several billion instructions per second. But early computers, like the Manchester Mark I, helped to make this possible. In this lesson, we're going to focus on the way the contents of various CPU registers change while a program is running. Before we do, let's briefly recall that a register is an arrangement of logic gates inside the CPU capable of storing a group of binary digits. A register's contents can change millions of times a second while a program is running, so it has to be designed for quick access. You can see a representation of a 16-bit register here, but these days a register inside a modern CPU can store 68 bits or even 128 bits. These are the names of the CPU registers that we're going to visualize in action. If you're a student of computer science, you should be able to describe the purpose of each of these, and you should know what each one might contain. To see how these registers interact with each other, we're going to look at the execution of only a small fragment of a computer program. Here's a line of code written in a high-level programming language. This language could be VB.NET, Ruby, Python, or something else. A simple instruction like this looks very similar in lots of different programming languages. Before any high-level code can run, it has to be translated into machine code, binary ones and zeros, because that's all the CPU can understand. With some high-level programming languages, like VB.NET for example, the entire program has to be translated into machine code before it can be executed. This method of translation is called compilation, and it's done by a special utility program called a compiler. With other languages, such as Python, one high-level instruction is translated into machine code, then executed, before the next instruction is translated. This method of translation is called interpretation. Compilers and interpreters usually come with the software tools used by programmers. Most compilers and interpreters convert high-level code into an intermediate form of low-level code first. Each high-level instruction becomes many low-level instructions, but then each low-level instruction becomes only one machine code instruction. During translation, variable names are converted into numeric memory addresses, resulting in an even lower level of instructions called assembly code. The instructions you can see here tell the CPU to take a copy of whatever is in memory location 3 and load it into the accumulator. Then add a copy of whatever's in memory location 4 to what's in the accumulator. And then finally to take whatever's in the accumulator and store it back into memory location 5. By the time the translator has generated assembly code like this, it's done most of its work, so converting it into binary machine code is a very easy final step. By the way, every type of CPU has its own set of commands that it recognizes. For example, LDA, STA, add, and a few others. These are known as the instruction set of the CPU. This means a compiler or interpreter not only has to understand the high-level language that it's translating into machine code, it also has to know the instruction set of the CPU that it's generating the machine code for. If you're compiling a program to run on a PC and a Mac, for example, you're going to need two different compilers. Anyway, because there's a one-to-one correspondence between assembly code instructions and machine code instructions, it's convenient for us to imagine the CPU executing assembly code rather than machine code. So let's visualize these instructions being executed and look in detail at what happens during the fetch, decode, execute cycle. We're going to need a central processing unit with a control unit and an arithmetic and logic unit. The program counter and the current instruction register are located inside the control unit. The arithmetic and logic unit contains the accumulator. We also have the memory address register and the memory data register. Where these are depends on the design of the CPU. For now, we're only really interested in what these registers do, not exactly where they are. This is, of course, a greatly simplified model, that is, an abstract model. For example, this particular CPU has only a single core, but dual-core and quad-core CPUs are very common these days. We're also ignoring a lot of other components, including various other registers and the different levels of CPU cache, for example. A CPU on its own would be useless without the main memory to store programs and data. This is the random access memory, or RAM for short. The word random simply means it takes the same amount of time to fetch something from the memory, regardless of where it is in the memory. Random access is just another way of saying direct access. All access to the memory is controlled by a circuit called, guess what? The memory controller. Each memory location has an address. Memory addresses are numbers ranging from 0 to, well, something very big, depending on how much memory is available. Even a typical 8 GB of RAM has over 8 billion memory locations and therefore over 8 billion memory addresses. The CPU is connected to the RAM by a set of parallel wires called the data bus. It's also connected by the address bus and the control bus. It's worth mentioning now that almost everything that goes on inside the computer, including the workings of the CPU, is regulated by the system clock. This is not a clock that can tell the time, rather it's a very simple device that continually generates a rapid sequence of very regular electrical pulses. All movement of instructions and data during the fetch, decode, execute cycle are synchronized to the system clock, and the faster the clock speed, the faster a program will run. Our program instructions have already been loaded into the main memory. This is taken care of by an operating system, such as Windows 11, when the program is launched by the person using it. These instructions are, of course, stored in binary machine code, but it's convenient for us to visualize them like this. Each of these instructions refers to a memory location by its address. LDA3 tells the CPU to load whatever's in location 3 into the accumulator. So let's put some data into location 3. Add4 tells the CPU to add whatever's in location 4 to whatever's in the accumulator. So let's put some data into location 4 as well. The program counter inside the CPU already contains the memory address of the next instruction to be fetched. Remember, these 3 instructions represent only a fragment of a program, so the CPU may be halfway through it by now, or it may be very near the start. To fetch the next instruction, the memory address stored inside the program counter is copied into the memory address register. This makes it available to the address bus, so it can be copied to the memory controller. Now, the control unit issues a read instruction to the memory controller via the control bus. The CPU wants to read something from the memory. The contents of memory location 10 are put onto the data bus so they can be copied into the memory data register. And from there, because it's an instruction, it's copied into the current instruction register. Now that the first instruction has been fetched, 1 is added to the value of the program counter. The program counter is incremented. so the program counter already contains the memory address of the next instruction to be fetched before this one has even been processed. Now the instruction load 3 is decoded. We're not going to go into detail about exactly what that means now, but suffice to say, various electronic circuits composed of logic gates are switched on, circuits which will carry out the instruction. The purpose of this instruction is to load a copy of whatever's in memory location 3 into the accumulator. It involves reading something from the memory again. So the control unit puts the memory address, 3, into the memory address register, overwriting what's already there. This makes it available to the address bus and it's copied to the memory controller. A read instruction is then issued. The contents of location 3, the number 20 in this case, are copied to the data bus and then to the memory data register, overwriting what's already there. And from here it's copied into the accumulator. So that's the first instruction, fetched, decoded, and executed. To fetch the next instruction, the contents of the program counter are copied into the memory address register. This is then copied to the memory controller via the address bus, and a read instruction is issued by the control unit. The second instruction is placed on the data bus and copied into the memory data register, replacing what was already there. And from there, because it's an instruction, it's copied into the current instruction register. And the program counter is incremented. The new current instruction can now be decoded. In other words, the control unit will engage whatever circuitry is needed to carry it out. This instruction will add the contents of memory location 4 to whatever's in the accumulator, so the memory needs to be read again. The memory address 4 is put into the memory address register and sent to the memory controller via the address bus. A read instruction is issued and the contents of location 4, the number 30, is copied to the memory data register. As you can see, whenever the memory is read, a memory address has to go into the memory address register first, and whenever anything enters the CPU, it has to come through the memory data register. The number 30 is now passed to the arithmetic and logic unit, which will switch on the appropriate circuitry to add it to the value that's already in the accumulator. The program counter was previously incremented, so it's already pointing to the next instruction to be fetched. The contents of the program counter are copied to the memory address register. From here, they're copied to the memory controller via the address bus, and a read instruction is issued. The instruction at memory location 12 is put onto the data bus and copied into the memory data register, replacing what was already there. From here, it's copied to the current instruction register. Immediately after the fetch, the program counter is incremented, so if there's another instruction to be had, it's already pointing to it. The store instruction is slightly different from the previous instructions. This time, the CPU is going to write something to the memory rather than read something. The instruction says store a copy of whatever's in the accumulator into memory address number 5. Well, we're going to access a memory location, so, as before, the memory address has to be put into the memory address register and sent to the memory controller via the address bus. In order to execute this particular instruction, the contents of the accumulator are copied to the memory data register. Anything moving in or out of the CPU has to go through the memory data register. A write instruction is then issued by the control unit, and the data is copied via the data bus into memory location 5. And that's the program completed, or at least this very small fragment of it. Here's a summary of some of the events that take place during the fetch, decode, execute cycle. This list is focused on the fetching of instructions, but of course data items that the instructions work with can also be fetched and saved to the memory. If you're a student of computer science, you might want to pause the video now and take this information down, so you can revise it later. And here's a summary of the purpose of each register that you've just seen in action. The program counter stores the memory address of the next instruction to be fetched from memory, before the current instruction has even been decoded and executed. The current instruction register stores the instruction that is currently being decoded and executed. The memory address register stores the memory address of the instruction being fetched from the RAM, or the data item being fetched from or saved to the RAM. The wording of this description makes the point that program instructions are only ever fetched from the RAM, but data items can move in both directions. You might have also noticed that memory addresses only ever travel in one direction, from the CPU towards the RAM. We say that the address bus is unidirectional, but the data bus is bidirectional. The memory data register stores the actual instruction being fetched from the RAM, or the data item being fetched from or written to the RAM. Again, the wording is important. It implies that data items can move in both directions, but instructions only ever come from the RAM. And finally, the accumulator stores the intermediate results of calculations. Again, if you're a student of computer science, you might want to pause the video now and take these notes down so you can revise them later.